Good evening, sir. Today we are going to discuss my TP assignment, and today we have taken 4 questions. So we will see it one by one. So my first question is determination of viscosity from capillary flow data. Glycerin at 26.5 degrees Celsius is flowing through a horizontal tube 1 feet long and width 0.1 inch inside diameter for a pressure drop of 50 psi. The volumetric flow rate W by rho is given. The density at 26.5 degrees is 1.261 gram per centimeter cube. From the flow data, find the viscosity of glycerin in centipoise and in Pascal second. Okay, so now we will solve. So in this question we are going to use Hagen-Poiseuille equation, and this equation is nu is equal to pi p naught minus pl into r to the power 4 upon 8 w upon rho into l. So on substituting the values given in the question, we get the answer coming out to be 4.92 gram per centimeter second, equal to 492 centipoise or 0.492 Pascal second. Now we have used the Hagen-Poiseuille equation. So here is the derivation for the Hagen-Poiseuille equation, which comes under flow through circular tube. So here is the theory regarding circular tube, that we consider steady state laminar flow of a fluid of constant density and viscosity in vertical tube of length L and radius r. The liquid flow downward under the influence of a pressure difference and gravity. Figure we specify that the tube length is very large with respect to the radius, so that end effects are neglected. Here we define Vz is equal to function of r, Vr is equal to 0, V theta is equal to 0, and P is function of Z. So tau Rz is equal to tau Zr is equal to minus nu dVz upon dr. Now we select our system as cylindrical shell of thickness delta r and length L, and we begin by listing various contribution to Z momentum balances. So here the rate of Z momentum in across annular surface at Z is equal to 0 is 2 pi r delta r phi zz at Z is equal to 0, and rate of Z momentum out across annular surface at Z is equal to L is 2 pi r delta r phi zz Z is equal to L, and rate of Z momentum in across cylindrical surface at R is 2 pi rl phi rz at R is equal to 2 pi rl phi rz at R, and rate of Z momentum out across cylindrical surface at R plus delta R is 2 pi r plus delta L phi rz at R plus delta R is equal to 2 pi rl phi rz R plus delta R, and gravity force acting in Z direction on cylindrical shell is 2 pi r delta L rho g. Now coming to next page, here is the reference diagram we have used for this derivation, and the momentum balance on applying we get this 2 pi rl phi rz at R minus 2 pi rl phi rz at R plus delta R plus 2 pi r delta R phi zz at Z is equal to 0 minus 2 pi r delta R phi zz at Z is equal to L plus 2 pi r delta RL rho g is equal to 0. Now when we divide this equation by 2 pi L delta R and take the limit as delta R tends to 0, we get this equation, and the expression on left side is definition of first derivative. Like when we take the derivative of this with respect to R, we get this equation, and evaluating the components phi rz and phi zz, we get phi rz is equal to tau rz plus rho v1 v2 is equal to minus nu dvz by dr plus rho Vz Vr, and phi zz is equal to this. Also Vz is function of R, Vr is equal to 0, and V theta is equal to 0, and P is function of Z. Then we make following simplification. So we get this equation. Okay. Now upon applying the boundary condition and first of all integrating, we get tau rz is equal to p naught minus pl upon 2r 2l into r plus c1 upon r. Now constant c1 is evaluated by using boundary condition. Boundary condition 1 at r is equal to 0 is equal to tau rz is equal to infinite, and c1 is equal to 0, and tau rz is this. Now applying Newton's law of viscosity, tau rz is equal to minus nu dvz upon dr. On equating both sides, this and this, we get this equation, and for constant c2 boundary condition 2 we apply. So the constant C2 is get by boundary condition 2 at R is equal to R, Vz is equal to 0. From this we get P naught minus PL R square upon 4 nu L. Hence the velocity distribution is given by this equation. Once the velocity profile has been established, various derived quantities can be obtained. Okay. So here the maximum velocity is given by this equation. The average velocity is obtained by dividing the total volumetric flow rate by cross sectional area. Okay, so now this is the expression for that. The mass flow rate W is the product of the cross sectional area pi r square, the density rho, and average velocity Vz. So W is equal to pi p naught minus pl r to the power 4 rho upon 8 nu L. This is the required Hagen-Poiseuille equation which we derived. It is used along with experimental data for rate of flow and modified pressure difference to determine the viscosity of fluid in capillary viscometer. Now to check whether the flow is laminar, we calculate by using Reynolds number. When we put the given data from the question, we find out Reynolds number to be 2.41. Hence the flow is laminar. Also the length comes out to be 0.0007 feet. Now we come to second question. This is based on scaling up of a agitated tank. So here we take experiment with a small scale agitated tank used to design a geometrically similar installation with linear dimension 10 times as large. The fluid in the tank will be heavy oil with nu is equal to 13.5 centimeters and rho is equal to 0.9 gram per centimeter cube. The large tank is to have an impeller speed of 120 rpm. Determine the impeller speed for the small scale model in accordance with criteria in example 3.72. Determine the operating temperature for model if water is to be used at stirred fuel. Okay, so now we on with solution. The specification for operation are given. N1 is equal to 120, U1 is equal to 13.5 and rho 1 is given, and the tank is operated with this given condition to allow direct prediction. So to meet the latter requirement, therefore we are going to use this equation d2 n2 square is equal to d1 n1 square. Then as usual, gravity is equal for both, then model must operate at n1 comes out to be 120 root 10 is equal to 380 rpm. Also require this equation. On substituting, we get v2 is equal to 0.474 centipoise. We see that value of this correspond closely to the value of liquid at 60 degree. Thus model should operate at 380 rpm, liquid at nearly 60 degree. Derivation, how to derive this equation we have mostly used, and in which the Reynolds number is d square n rho by nu and fr is equal to d n square upon g. For time smooth observation at last t, the dependence of t disappears. Therefore d1 square n1 upon v1 is equal to d2 square n2 upon v2. So here on substituting the gravitational force, we get this, and the gravitational force on both are same, so we get final equation this, which is the required equation. Now when we come to another question, prediction of thermal conductivities of gases at low density. So this question is based on thermal conductivity. Compute the thermal conductivity of argon at 100 degrees Celsius and atmospheric pressure using the Chapman-Enskog theory and Lennard-Jones constant derived from viscosity data. Compare your result with observed value of this. Compute the thermal conductivity of NO and CH4 at 300 Kelvin and atmospheric pressure from the following data for this condition. These conditions are given, and this table we have NO and CH4, new values given, and CP is given. Compare a result with the experimental value. ठीक है. Since argon is monoatomic, we use this equation to predict this K. This is the main equation we are using for determining the value of K. And here T is equal to 100 plus 273.15 is equal to 373.15, and table gives us M is equal to 39.948 and sigma is equal to 3.432 Armstrong, and epsilon upon K is equal to 122.4 Kelvin for argon. Then KT by epsilon is equal to 373.15 upon 122.4. Substituting this value, we get 3.049. Now on interpolation, we get the omega nu comes out to be 1.0344. Then equation gives us this value, which is within 1.5% of observed value. Therefore equation Euclide's formula gives K is equal to Cp plus 1.25 R upon M into nu. Also this with R is equal to 1.98 calorie per gram mole Kelvin. Insert this data for Cp and nu. For M from table gives for NO K is equal to comes out to be 0.02595 versus 0.02590. This is the experimental value, whereas this is the theoretical calculated value. For CH4 same, K is equal to 786 into 10 to the power minus 7 calorie per 7 centimeter Kelvin versus 0.03427, which is experimental value, and this is calculated value. Now we see here the derivation for thermal conductivity of gases. For rigid sphere gas, we know mean molecular speed is given by this, the Z wall collision frequency per unit area is this, and mean free path is this. The molecules on reaching any plane had an average of distance A is equal to 2 by 3 into lambda, where K is equal to Boltzmann constant and N is equal to number of molecule per unit volume, M is equal to mass of molecule. The mean transitional energy per molecule under equilibrium constant is half m nu square is equal to 3 by 2 kT. Also for such gas, Cv is equal to du by dt at constant volume is equal to n d by dt half m nu square is equal to 3 by 2 R, in which R is the gas constant. Equation is satisfactory for monoatomic gases. Now to determine thermal conductivity, we examine the behavior of gas under a temperature gradient. The heat flux across the plane is found by summing the kinetic energy of molecules across the plane per unit time in y direction and subtracting the kinetic energy of equal number that cross in the negative y direction. So this comes out to be this, and temperature profile is given by this. And the temperature profile is linear for a distance of several mean free paths, and the temperature y minus a is equal to temperature at y minus 2 by 3 lambda dt by dy, and temperature at y plus a is equal to given by t at y plus 2 by 3 lambda dt by dy. Now applying Fourier's law of heat conduction with thermal conductivity, k is equal to half n ku lambda is equal to 1 by 3 rho cv nu lambda for monoatomic gases, in which rho is equal to nm is gas density and cv is equal to 3 by 2 k upon m. Substituting nu n lambda, we get this we get, okay, 2 by 3 lambda pi m kt upon pi d square into cv for monoatomic gas. Okay, now the Chapman-Enskog formula for the thermal conductivity derivation, we have derived this 25 by 32 pi m kt upon pi sigma square omega k cv cap, or k is equal to this. Also for monoatomic gases, the parameter sigma and epsilon deduced from the viscosity measurement. When we substitute this data on finding out, we get k is equal to 15 by 4 r by m nu is equal to 5 by 2 cv nu for monoatomic gas. Similarly for polyatomic gas, we have this. Now we come to the last question, which is taken from another book of Ismail Tosun. Oil spill on water can be removed by lowering a moving belt of weight W into the water. The belts move upward and skims the oil into a reservoir aboard the ship as shown in the figure. So this is the reference figure. Okay. Now what is asked? Show that the velocity profile and volumetric flow rate are given by this and this. Okay, and now determine the belt speed that will give us 0 volumetric flow rate and specify the design criteria for positive and negative flow rates. So first of all, we define the coordinate system that x is thickness direction belt to oil, from belt to oil, and z is along the belt direction of flow. Okay, assumptions: steady state flow, laminar flow, vz is a function of x, p is constant, gravity acting perpendicular downward, component only acting is g cos beta, no slip at belt surface. Now we are applying momentum balance in z direction, we get this on applying momentum balance. Now solving the differential equation, we get d square vz upon dx square is equal to minus rho g cos beta upon nu. Now integrating this equation, we get this, and now on integrating it twice, we get this c1x plus c2, another one constant. Now applying boundary condition for solving. Boundary condition 1, at x is equal to del shear stress is equal to 0. Now substituting this, we get del vz upon dx is equal to 0, and substituting this in here, we get this, and c1 value comes out to be this. And boundary condition 2 applying, we get x is equal to 0, vz is equal to minus v, we get c2 is equal to minus v. Then now for velocity profile, final velocity profile on substituting constant comes out to be this, and on rearranging we get this. Hence result are same and matching. Now for volumetric matching as per the question which was given to show. Now for volumetric flow rate, we add velocity across entire thickness q is given by w integration 0 to del vz dx. On solving it, breaking into two parts, part 1 for gravity is this, and part 2 for the belt is come out this. Final q is given by w rho g del cube cos beta upon 3 nu minus w v delta. Hence result are exact, same and matching as per the question data given. When for part B, when flow becomes 0, set q is equal to 0, we get this. On cancelling w and delta on both sides, this and this cut, so we get the critical velocity comes out to be this. This is required equation for critical belt speed. Criteria is given here. If v is less than critical velocity speed, gravity dominates and oil falls downward, and q is greater than 0, and if v is equal to vc, net flow is equal to 0, and third is v is greater than if vc, belt dominates and oil is lifted upwards with q is less than 0.